My new loop antennas seem to be quite popular. Here comes a dimensioning tool for all frequency ranges. The loop antennas described here should not be confused with so-called magnetic loop antennas, which are often used in amateur radio. The circumference is exactly one wavelength, so they become relatively large at low frequencies. Magnetic loop antennas are much smaller, so please do not confuse. The antennas shown here are intended for frequencies from 100 MHz to 5 GHz, which corresponds to an antenna diameter of around 2 centimeters to 1 meter. What I particularly appreciate about these antennas is that they are a bandpass filter and an antenna at the same time. In previous videos, we presented DIY loop antennas for the 866 MHz LoRa frequency band. My viewers now asked questions about dimensioning the antennas for other frequency bands. After we already saw in the last video how to dimension a matching network, I decided to develop a small Excel tool with which you can dimension the complete antennas for any frequency band yourself. And yes, don't forget to like the video and subscribe to the channel. Based on the frequency and the diameter d of the conductors, all other parameters shown here can be calculated. I will demonstrate the tool using a new example. It's about dimensioning a loop antenna for the 2.4 GHz band, namely for the copper wire solution and the foil or printed circuit solution. In a later video, I will show the realization and then analyze the antennas with a vector network analyzer. Okay, here we go with the tool, which you can download as always. It's basically an extension of our tool for calculating an impedance matching network. I will link you the video on the top right. It explains how the principle of waveguide impedance matching works. I have just added 3 sheets to this Excel tool for the dimensioning of the antennas. We don't need the original sheets for our sizing though, but I left them in because they fit the theme very well and the dimensioning tool builds on them. Let's check out the synthesis wire loop sheet. I simply entered the exact parameters of the 866 MHz antenna that I have already built. The link to the video is at the top right. And yes, the tool calculates the impedance of the arrangement right away. It is not quite ideal, but it is a good impedance match at 50 ohms. As said, we want to build a 2.4 GHz antenna. So at the top we put f equal to 2400 MHz. We have provided a copper wire with a diameter of 1 mm. So we enter 1 mm for D. The tool immediately calculates the impedance, including the impedance matching network. Of course, we are not satisfied with these impedance values. It wouldn't be a good match at 50 ohms. We can now change the remaining parameters, the spacing of the waveguide wires, and the angle alpha, which defines the exact point of the feet. We can now change these two parameters until an optimal adjustment is achieved. Of course, we let the computer do that, because finding the optimum for two parameters takes a lot of trials. Not really fun to do that manually. We better use the solver plugin. In the lower area, I have prepared everything for it. We have a cost function at the bottom. We feed this field into the solver and require the value of the cost function to be 0. We enter the two cells for the wire spacing S and the angle alpha as variable cells. Then we start the solver using the CRG method. And a second later we get an impressive result. The impedance is exactly 50 ohms plus J0 ohms. This is an ideal impedance match. Cool! And we can now read the ideal wire spacing S and the ideal angle alpha here. In a later episode we will build and measure an antenna exactly according to these specifications. If you want to build a number of identical antennas, then of course it makes sense to build them as a printed circuit board or from foil. That's why I developed the synthesis band loop sheet. The functionality is exactly the same as with the wire loop antenna. Let's try out with our new example. So we enter the frequency 2400 MHz. The width of the conductive tape that makes up the ring should be 8 mm. With the solver we now vary the size of the gap S between the conductors and again the angle alpha that marks the feed point. The result is again a perfect fit, and we can read the size of the gap and the angle alpha. I have summarized the results for the design of the antennas for the 2.4 GHz frequency here. As you can see, the angle alpha is not exactly the same in both cases. The reason for this is mainly the different impedance of the loops. With the design, you will certainly not hit the resonant frequency exactly. A little tuning will still be needed for the real antenna. I'm really looking forward to the measurement results. Now I just have to explain one little thing. You may have noticed that the tool also calculates the impedance of the conductive loop ZA. And that's actually not that easy. I used a functional approximation for this. I have already built and measured various loop antennas. With the methods we talked about, I then determined the impedances of the antennas and presented them in the graphic. It actually consists of just 3 points that I connected with the blue curve. Now that I would like to have a continuous function to calculate the impedance of the loop, I had to do a functional approximation. It works like this. I used an exponential function with 2 parameters that I just guessed at a starting point. We see from the orange curve that the agreement with the measured values is not good at all. With the solver, I can find the right parameters here that I can continue to use. I then use the exponential function with the found parameters to calculate the impedance of the loop depending on its conductor thickness. The insights. High frequency engineering can get complicated. This is particularly the case when one wants to exploit resonances. Then certain current and voltage levels are distributed along the conductor, and it is not easy to calculate what effect the connection has at a certain point. However, with the small Excel tool, you can now calculate a lambda loop antenna, including the associated matching network for any frequency. This is always a good start if you want to make such an antenna. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.